Hello and welcome to part 1 of lesson 1 in this game development series. In this part we're going to talk about the basics, so some simple language things and some stuff to do with compilation and linking, before in the second part we move on to the ramifications that this stuff has for getting SDL working and linking graphics libraries and things like this. I'm planning to go through every line of code on the screen here and explain some basic stuff about C++, which some people manage to get by without knowing. If you've only ever used an IDE, like CodeBlocks or Visual Studio, some of the latter stuff should be new. We'll start basic and zoom through lots of different language features. If you're an experienced programmer, this may be old hat. If so, there are some timestamps in the video description, so you can move to the important stuff. I'd recommend sticking around for the bit on compilation and linking. I'll say now that this is not a complete overview of the language. I'm not going to go into classes or templates or whatever. Instead, it's some important stuff that we'll need to keep in mind during later tutorials. Think of it as a refresher so that we're all on the same page in later stuff. So, if we think of programs as basically made up of data and operations on that data. Everything else is an abstraction that we've built on the language so we can better understand what's going on. In C++, there are a number of built-in variables with set types which contain this data. We have the arithmetic types, which consists of bool for true-false data, char or char for character data, and this is basically just a number mapped to the ASCII character encoding scheme, int and its various friends for standard numbers, and float and double for numbers with decimal places, and very, very big numbers, what we call floating point numbers. We also have pointers and references. If you don't know what these are, you should go and find out, because it's super important. Now, if we want to do complex operations to these bits of data, which we will, it's useful to have things like control statements, which direct and modify the flow of the program, and also conditional operators. In C++, we have a range of these. For and while loops, if and switch case statements help to control the flow of the program, and there are a large number of conditional operators, the same kind of things that are used in other languages and also mathematics. So having placed variables and control statements in our grab bag of useful things, we might also want to split our program up into smaller, easier to understand chunks. There are two main ways of doing this in C++. Functions and classes. Functions are a nifty way of moving a series of statements from the main program into their own little box. This is really useful if we're typing the same thing over and over again. Instead of writing that code many times and being open to error, we can just call the function. So this first block of code here defines a function which returns an integer and takes two integer arguments. It just assigns the second argument to the first and returns it. This bit of code here calls the function through the brackets operators and returns the result as an initialization to this integer here. Obviously there's a lot more to how functions work, but we'll cover that as it comes up. Classes are incredibly complicated and there are a large number of features to consider. Basically, they provide a way to encapsulate data and functionality. In other words, we can gather together variables and functions, accessing them using an interface that we've designed. We'll learn a lot more about how these are used later on. So, if we go back to the top of our program, we can already see a number of these features at work. Line 11 defines and initializes an integer variable. Lines 12 through 14 are using a for loop. There are three functions on the page. Line 13 is a printf function, writing to the console. Line 6 is calling a function which was declared on line 3 and defined on line 10 through 15. And there's also a function defined on lines 5 through 8. Unlike some other programming languages which begin execution at the beginning of the code file, like Python, a C++ program begins inside a function named main. This function returns an integer to the operating system to indicate success or failure. This is usually 0 for success. This main function is like any other function you may write in C++, by which I mean it can have arguments, and indeed it does. You might not see them sometimes, but they're there. These are usually called argc and argv, but it doesn't really matter what you call them as long as one is an integer and one is a pointer to an array of characters. The program will still run if you give them a different type, but it won't behave as you want it to. So having gone through all of that, there are three things which remain somewhat of a mystery. The first is that if we haven't defined this function here, printf, where has it come from? How can we just use it without ever telling the computer what it is or what it does or how it works? The second is this mysterious green line at the top of the file. What does #include standardIO.h mean? You may know that you need to include this line in order to use this printf function, but like, what's going on behind the scenes? And the third thing is, what's going on with these arguments to main? Why do they exist, and what should we do with them? To answer these questions, we have to move a little bit beyond the scope of the IDE. IDEs often abstract what's really going on when you press the build and run button. Sometimes it's much easier to throw away the IDE and start from scratch. Rather than typing our program inside code blocks, I'm going to copy it, open a text file, paste it and save it as main.cpp, so with the CPP file extension. And what I've created here is a source file, and here it is, main. Somehow, CodeBlocks, or whatever IDE you're using, has found a way to turn this text file into an executable. That is, a file which can be run by the computer. When you press the Run button inside your IDE, you're simply running the executable file. So, what is doing the conversion between this text file and the exe? Well, it turns out that the answer is just another program called a compiler. I can check which compiler I'm using in CodeBlocks by going to Settings, Compiler. You can see that I'm using the GNU GCC compiler. If you're using Visual Studio, you're probably using the Visual C++ compiler. If you're working on a Mac or a Linux system, you'll also be using the GNU GCC compiler. It's open source. We can actually view where that program resides. On my computer, it's within the CodeBlocks installation file, inside min.gw, bin, and GCC. There it is. This program, G++, changes our text file into an executable. CodeBlocks is simply running our text files through that compiler. If we want to, we can do the work ourselves on the command line. Now, the command line is a little program which used to be used a lot more on Windows, but it's still used quite a lot on Mac and Linux systems. Now, in order to run our text file that we made earlier, we need to add the GNU compiler into the system path, so the command prompt can see the compiler, basically. So we open my computer, right-click, Properties, Advanced System Settings, Environment Variables, and inside this box, look at Path, and then click Edit. And at the end, you want to put the wherever your compiler is located. So in my case, the GNU GCC compiler is within the CodeBlocks installation file system. If you haven't got the GCC G++ compiler, you can find it somewhere else. Note that if you're not using Windows, your command prompt will have all of this stuff automatically installed, so you don't need to do that. So now that I've done that, I want to navigate to the desktop, and I'm going to type dir, which is going to tell me that the main.cpp file that I made earlier is right there. And we can check that the compiler is working by typing g++ -- version, which will give us some spiel about what version the compiler is right now. So now let's type in g++ main.cpp. And what this will do is g++ will take that file and make it into an executable file, which by default is named ea.exe and is in the same directory as the file, as the source code. So we press enter, and then we check again, and there it is, a.exe. And if we run it, we're going to get the hello world stuff, so this is great. Now, if we go back to CodeBlocks, rebuild the project, and look at what's going on in the build log, much the same thing is happening. Here we're calling the ming.gw32-g++.exe compiler, which is also in this folder, It's down here. And it's basically the same thing as G++. And we're running it on the main.cpp file here. And it gives us the full path there. However, there's a lot more stuff happening than we've covered. All these words beginning with dashes are what we call command line arguments. They specify to the compiler what behavior we require. -wall, for example, turns on all warnings. Warnings all, wall. So, on compilation, the compiler will tell us everything that's wrong with our program. The -o argument specifies where we want the output file to be and what it will be called. I mean, we can implement these ourselves on the command line. If we type in g++ main.cpp -o, we can then choose what we want the output file to look like. So instead of being a.exe, we can change it to main.exe, and then run that file, and it's hello world again. All this work allows us to solve one of our problems, namely, what's happening with the arguments passed to main. So I've made a little file called main arguments, which is simply printing the argc and printing the first array in this array of arrays. So if we go back to the command line, g++ main arguments.cpp, and give it the output of, let's call it file.exe, and then we run it, we'll get the result of 1 and file.exe. I mean, why it's giving us this is because argv is an array of arrays, and this integer tells us how many arrays there are inside this array of arrays. And the first array is always the name of the file itself. So we can rewrite this code as a for loop, so that we can print everything within the array of arrays, like this. And if we run that again, it's going to give us the name. And you can also pass things into your program by providing them as command line arguments to the executable file. So if you go file.exe and then you type something afterwards, like gibbon nipples, that's going to get passed into that array of arrays. And since our program is printing all of the arrays within that, it's going to give us gibbon nipples back. So that's what these arguments are to main. So to solve our final problem, the mysterious green text, we need to know a bit more about the compilation process. So here is a flowchart of what actually happens, rather than what I've been lying to you and simplifying. What we recognize already is the source code here, the compiler here, and the executable here. But there's a whole load of gubbins in the way. It turns out that the compiler doesn't actually compile the source code directly to an executable file. Rather, it turns the source code into something called object code. Then a separate program, called the linker, comes along and ties together all the object files into the final program. We can split this process up on the command line by using the -c argument. This creates an object file which we can separately compile. The reason why this is useful is that many large projects contain multiple source files. In order for one source file to reference another, they all need to be linked into one big file at the end. We can do this ourselves by moving the printlines function from the main.cpp file into its own file, a printlines.cpp file. And there we go, here we have it. And now if we try and compile this, so we go g++ main.cpp printlines.cpp -o main.exe, it's going to tell us that printlines was not declared. The main.cpp file still can't seem to see the printline function. What we need to do is declare the function within the main.cpp file. This tells the compiler that there's a definition of the function somewhere else. It just needs to hang tight until the linker gets around to supplying the code, and it'll all be fine. So you see in this flowchart right there. So then if we declare the function Do it again. It'll work. And then we can run it, and it'll do it. So there we go. However, normally, we wouldn't declare everything repeatedly in the different source files by themselves. This is annoying and error-prone. Instead, we create things called header files, which contain all the declarations for us. We can do this now. So if we make a new notepad file, and we just write void printlines into it, and we'll save this as printlines.h. And then we can write include printlines.h. And then we can compile them again and run it. Great. So this works, and also, aha, we've solved our green text problem. It appears as if standard.io.h is just another bunch of declarations, just like our printlines header file, one of which is probably the printf function, and at some point in the compilation process, the linker will include the relevant source code. That's what this libraries means on the diagram. As one last thing, the program which includes the header files is not really part of the compiler or the linker. It's a separate thing called the preprocessor. This program runs through all the files and literally copies the header files directly into each source file. And it does that right before the compiler gets to work on it. So we covered quite a lot in this part. The important stuff that we covered was the stuff to do with linking and compiling, and the whole kind of pipeline of how the compiler goes about doing things. So you write your source code, which is a .cpp file. Your preprocessor goes through and changes all of the code to how it needs to. The compiler changes that code into object code. The linker picks up the object code that you've written, links it all together, links it in with the various libraries that you've included, and then it turns all of this into an executable file, something that that Windows can run, or whatever operating system you're using. So once we know all of this, it becomes a lot easier to get STL working on a system. And this is what part 2 will talk about.